Hello, today we will use STAAD to solve a compound beam. And this is the example that we will do in the class by hand calculation. And today we will use the software STAAD Pro to find the support reaction at A and support reaction at B. And our purpose is to compare the results with hand calculations. And this compound beam has 3 nodes, and A is a roller support, C is a hinge connection, and B is a fixed support. And this beam subject to a point load on member AC and a uniform load 8 kilonewton per meter on member CB. And instead, we will use node 1 to represent node A, and use node 2 to represent the hinge connection at C, and node 3 to represent the fixed support at B. So let's go to the STAAD Pro. So after you open the software, and this is the interface of STAAD Pro software. Okay? And for first thing we will do is use configure, and this configure, click configure, and this is the place that you actually set up the base unit system. And we need to compare the original example and what's the base unit. And let's go back to the example. Okay? And for this example, we notice that dimension is meters and the load is kilonewton. So for this original example, is the metric system. And instead, we choose metric. Okay, choose metric for base unit system, and this must match the original example. And for the remaining, like the language, we just use default English, and the global axis, we use Y up. So in a 2D model, we just show the XY plane, and Y is upward is positive. And then the remaining, just use the default. It won't affect the analysis results. Okay, so after that, we click OK. Then we go to New. And for a new model, and for the new model, we find this window has 3 tabs: model information, job information, and create. And we will do in this order. And first, model information. And we put the file name. And file name, for example, I just call this beam1. And then the location. And you will select the directory to save all the modeling file. Okay. So for example, I set up a folder to save the beam modeling files. So I select this folder, and the directory show up here at location. And then for the type, we just use the default analytical, and for the unit, double check as a metric to match the original model. Okay. And then go down to job information. And this job information, you just put something, the information for your own record, and it's also show up in the output file. Okay, so for the job, this one I want to see the beam modeling. Compound beam. Client, I put RIT. And for job number, and I just put the course number here. And we don't have any revision thing. And just leave this part blank. Reference as a class example hand calculations. And engineer, put your own name and enter the date. And for the comments, and for the example, the purpose is to check the support reactions at A and B. And our purpose is to compare the STAAD output with the results from hand calculations. Okay. And then we do not have any connect information. Okay. So just after the comment, you're done with job information, and then go down one and click create. And after click create, and it will guide you to this analytical modeling window. And under this analytical modeling window, and we will do a series of input. And for the analytical modeling, we will do the input in the order from left to the right. So we will do geometry, properties, materials, specifications, supports, loading, and analysis. So we just stop at analysis. We won't use anything for design. Okay, so this course is structural analysis. So we just use the STAAD software to do structural analysis part. So we will be done at analysis. Okay, so first analytical modeling, we will do the geometry first. Okay, so when you do the geometry, you need to refer to the original model. So let's take a look at the model. And for this beam, we have 3 nodes, 1, 2, 3. And we will manually input the coordinates of each node. And for 1, we input 0, 0, 0. And for 2, we have 4, 0, 0. And 3, we have 6, 0, 0. Okay, so this is a 2D model. So all the Z dimension is all the Z dimension is 0. And since this is a beam, the only difference among this 1, 2, 3 is the X coordinate. So we have 0, 4, and 6. Okay. So in this geometry window, and on the right-hand side, and we have this coordinate system, the table that you do the input, manually put the coordinate. So node 1 is 0, 0, 0, and 2 is 4, 0, 0, and 3 is 6, 0, 0. And after you do that, you will see the nodes show up in the screen, okay? Okay, so this is the 2D model, and default view here is a 3D, and you can see the coordinate system. This shows the positive X, Y, and Z direction. And I think it's easier just for 2D model, we just see the XY plane. Okay, so how to do that? We go to this top menu here, view, okay, view, and under this view thing, and you can see there's the cube with the face highlighted, and we will select this front view. Okay, so click that, and then you will see that we only see this XY plane. Okay, so after that, go back to this geometry tab. And back to geometry, after we input the nodes, And now we need to connect nodes to draw the beam member. So in order to do that, we use this add beam button right here, add beam button. Click that, and then your mouse just change to the add beam cursor. So after that, you just connect 1 to 2, and then 2 to 3. So you just draw the 2 beam members. Okay. After that, we're done with geometry, but your cursor still showed add beam. Now you need to hit escape, and now your mouse just change to the original. Okay. So we're done with geometry, and go to properties. And for this property, and the property window pop up, and for the original model, and we use W18 by 35. Okay. So this beam is statically determinate structure. So the section property will not play a role for results. So you can select any section properties to solve the problem, but in order to be consistent for the class example, and we use W18 by 35. Okay, so but you need to know that for statically determinate structure, and the results is independent of section properties and the materials. Okay, and for this W18 by 35, and this is the standard hot roll shape, and we can use the section database just right here, section database. After you hit that, this window pop up, and W shape is still, okay, W shape is still, and then we select this W shape, and in this window, you can go down, okay, to find the W18 by 35, and highlight that, and make sure that you check this material and steel, okay, this is steel beam, and to add. After that, you can see this W by 35 steel beam show up in this section window, and reference number 1, 18 by 35. Okay, so we just use this section for all the members of the beam. Okay, so now we close. And after you define it, we need to assign the section properties to every member in the structural system. Okay, so we need to assign this W18 by 35, and I will do here. Okay, so what I will do is assign to view, highlight 18 by 35, and then choose this assign to view, and then assign. It's just ask you that, are you sure to assign to the other members? I say yes. And then you can see that for both members, they have the R1. So R1 means reference number 1, which is section 18 by 35. Okay. And so make sure that every member in the system has a section property. We have 2 members, so you need to see that, okay, so we have 2 members all assigned to this 18 by 35. Okay, we're done with section properties. We're done with the properties, and then go to materials. And since we select W18 by 35, this is standard hot roll shape, so it's automatically set as a steel beam. So the properties default is steel, and we just accept it. Okay, so I just accept it, and you see the steel right here. So we're done with material. So make sure that every member in the structural system, you assign a material properties. Okay. Then we go to the specification, move to the right. So now first, I just uncheck. Okay, so you see that it's already select both beams. I just move my mouse anywhere far away from these two members and unselect the beams. And specification is a place that we can release the moment at a hinge connection. When we draw the beam, we from 1 to 2 and to 3. And when we draw this beam, every node, every connections is automatically set as fixed connection instead software. And for this example, we have node 2 is a hinge connection. So in order to remove the moment resistance, the difference between the hinge connection and the fixed connection is the moment resistance. So in order to remove the moment resistance, we need to use specifications. So specifications will use the beam option and release. And for member 1, we will use the location end because node 2 is at end of member 1. Then remove, release, MZ, check MZ, okay, because hinge connection doesn't provide any moment resistance, and do add. And you see that end MZ, so release the end MZ. Then we do the beam again and location start just for member 2, and also release MZ and do add. So for each hinge connection, make sure that you release the moment for each member that connected by the hinge. Okay, so after you create this release end moment and start moment, so now you need to assign this specification to each member. And so when we go to the specifications, it seems that we cannot see the nodes, okay? Especially the middle one, so which is node 2. So in order to accurately assign the release moment, I want to see where is the node 2. How to do that? I'll show you, okay? So put your mouse in the screen, right click. Then from the drop list, go to labels. And for the labels tab, make sure the nodes you turn on, node numbers and the node points. So check these two, node number, node points, and select OK. And now you can see the node number as well as the location of each node. Okay. So after that, I want to assign, okay, for the end, release the member end moment. I highlight that and use cursor to assign. And select assign and assign to member 1. So move your mouse to member 1 and escape. And now you can see a small circle close to the member end and left of node 2. So it means that for member 1 and this moment release is at node 2. And now we need to select the start MZ and use cursor to assign and assign to member 2. And then escape. So now you can see a small circle close to the node 2 on member 2. So it's a member start, release the moment. For each hinge moment, for each hinge connections, and you have to release the moment at each member that connected by the hinge connection. Okay? And for this example, we have 2 members connected at 2. So you need to release 2 times, 1 for each member. Okay, so make sure that you release the moment at each member connected at the hinge. Okay. So now we're done with specifications and go to support. And for support, this problem we have 2 supports, and one is a roller support at node 1 and a fixed support at node 3. Okay, so we need to create the 2 support. For this support window, and we click create. And first, let's create a roller support. And for roller support, we will choose fixed, but we use fixed but. And roller support doesn't provide any resistance in the X direction. So it's a free move in the X direction. I check Fx. And it's free rotate about Z axis. So I check Fx and Mz for 2D structural member. Okay, so check Fx and Mz. Release that for roller support. Then we do add. And you can see this support you just add is a roller support. Then we create fixed support. Luckily that we have this fixed support already built into this program. So we can just select this fixed option and do add. And you can see this fixed support. So now highlight the roller support and use cursor to assign and assign to node 1. Okay, then escape. Then highlight this fixed support. Use cursor to assign and assign to node 3 and escape. So now we're done with the support and move to the right, loading. And loading is to assign auto load on the structural members. So when we do the loading, the first thing we do is load case details. Highlight this load case details and do add. And for loading type, since this is the analysis model and we won't use that for any structural design, okay, so any type of loading is okay for this example. So for example, I just choose live load. Assume that the load on this beam is live load. So I just put a title, live load. And do add. So now you see this live load. See this live load, enter the load case details. We just use one load case for this example to keep it simple. And in the future, if you do structural design and you will have a list of load cases like the dead load, live load, snow load, earthquake load, wind load, and so on. Okay, and do each load case separately and then do the load combinations. But now we just keep it simple and do one case. So after that, highlight this live load case you just create and do add. And now we need add load items. And we have 2 load items. One is a concentrated load, 10 kilonewton on member 1, and the other is a uniform load, 8 kilonewton per meter on member 2. Okay. So both are member loads. So select these member loads, and then The first one is the point load. We'll use this concentrated force. And concentrated force, here's the input. And P is the magnitude. We put -10, -10. And negative means downward direction. And for direction, we just double check. And direction is global Y. Okay, GY means global Y direction, and global Y means upward is positive. So that's why we put a negative sign here. Okay. Then we have two dimensions, D2, D1 and D2. And for D1, here is illustration. And D1 is the dimension from the member start to the point load. So it's the distance from member start to the point load. And let's take a look at the model. And for member 1, we have this 10 kilonewton, okay, downward. So we put -10, and D1 dimension is from member start, which is node 1, to the point load. So D1 is 1 meter, okay, D1 is 1 meter. And D2 is eccentricity. D2 is eccentricity of the load. We don't consider any eccentricity in this model, okay? So we just leave the D2 blank, means that we do not have any eccentricity for the load across the section, okay? So just leave it blank, okay? So after that, we just do add. You can see that this concentrated load, GY, direction -10, and D1 dimension is 1. So after that, we need to add the second load items, which is member load, uniform force, and magnitude is -8. Again, negative means downward direction, and use global Y direction again, and D1, D2, D3, those dimensions we just keep at 0 if the uniform load occupied the entire member. And we know that this one, 8 kilonewton per meter, occupied the entire member 2. So we can leave D1, D2, D3 to all at 0. And if this uniform load only occupy a portion of member, and we have to give the dimensions, and D1 is from the member start to start of uniform load, and D2 is the length of uniform load, and D3 is eccentricity, and usually D3 is 0. There's no eccentricity. Okay, so then we do the add, and you can see the uniform load item show up under this live load case. So we just have 2 load items. I can close it, okay? And you can see those load actually with a question mark in front of each load. So it means that the program doesn't know where is this point load and do not know where is this uniform load. And we need to tell the program which member has the load. So highlight the concentrate load and use cursor to assign, and click assign and move your mouse to member 1 and then escape. You see the question mark gone. And then highlight uniform load and use cursor to assign and assign to member 2 and escape. So now you're done with the load assignment. Okay, you can take a look at, compare that with the original model and make sure those look correct. Okay, done with loading, and then move to the right. The last one, analysis. Okay, so I recommend you save your model frequently. I just, save in order to not losing any data. Okay. So for this analysis tab, okay, you see this analysis window pop up, and in this window, use define command, and this window analysis print command, and this window pop up, and print option, just use no print, and do add. Okay, so after you add that, you can see here, perform analysis, this command show up in the window. And this actually lets the program know that you want perform analysis. And this is very important. Make sure that you have this perform analysis, okay, command show up in this analysis window. So after that, we do close. And now actually you done with all those input data. And the next, you need to let the program know what type of output you want in the report. Okay, so now for output, you go up. Okay, so go up here, and this has post-analysis command. Post-analysis command give you the output, and click that. And for post-analysis print window, right here, we do define command. We need to let the program know that which one that you want the output, okay, which output you want. So define command, and there's many types of output in this window. And currently, and for this example, we only interested in support reactions. Okay. So for in output file, I want to see the support reactions. So I just choose the support reactions from the analysis print command and do add. And then close. And you find that after perform analysis, now you have this print support reactions command and with question mark. And for question mark, you need to let the program know that which support you want support reactions in output file. So I highlight print support reactions and then use cursor to assign and assign to node 1 and node 3. So for these two supports, I want the support reactions, and after that, escape. So now you're done with out input and output. Save your file, and now hit the magic button, Run Analysis. Okay, so after you hit Run Analysis, it takes a few seconds for the program to run, and you need target 0 errors, okay? And just neglect or ignore any warnings. So if there's 0 errors, means that you're good, okay? And then see that this is the 0 arrows for the running file, okay? So 0 arrows, and you choose View Output File right here. Okay, View Output File, and click down. Okay, So we'll share, this is the output file. Okay, so this is the output file. And then we click in this output file, we'll click this support action list. Okay, and so then you'll see that for support actions show up on the screen, and we have joint 1 represents node A, okay, and joint 3 that is the fixed support B, and for 1 is a roller support. For roller support, Fx is 0 and Fy is 7.5. Positive means upward, okay? And the remaining is all zeros. So for roller support, we only have one reaction force, which is y direction, 7.5. And for the fixed support B, which is the joint 3, and we should have 3 forces for fixed support, Fx, Fy, and Mz, okay? And for the force in the x direction, in this example, equals to 0 because there's no external x direction force. And force in the y direction is 18.5. Positive means upward. And Mz equals to negative 21 kilonewton meter. And here, negative means your sum, use your right-hand rule, and your sum point to the negative z direction. And if you take a look at the model, I just put the view in the 3D model, and you can see the positive z direction as a point to you, okay, point to you, and that's a positive z. And the negative z means your sum is point to the screen, okay? So negative z is point to the screen. And so your sum point to the screen, and then your fingers, just roll your fingers, and you find that the direction of rolling your fingers is clockwise. Okay, clockwise. So let's go back to the output file. And this negative 21, so means clockwise, 21 kilonewton meter. Okay, all those reactions match the hand calculations.